Hello everyone. Let's begin with a simple thought. When two people speak different languages, they can't communicate until they agree on some common gestures or signs. Similarly, when your program wants to speak to your computer's operating system or hardware, it also needs a common set of rules. And that set of rules is called as application binary interface or simply ABI. So when you write your C++ or Python code, it's like writing instructions in English. But your computers only understand binary, the language of zeros and ones. So when that human readable code is compiled, it must follow certain rules so that the compiled version can talk properly to other compiled programs and the operating system. And that's exactly what the ABI does. It defines how the compiled code interacts with other compiled code and with the machine itself. Think of ABI as the invisible translator between your software and the computer. Without it, even a perfectly written program would be like a traveler's in a foreign land, completely lost and unable to interact. So now, before we dive deeper, let's clear one common confusion. The difference between API and ABI. Imagine you are giving someone your recipe to make tea. You write the steps in plain words: boil water, add sugar, add tea leaves, so on. That's the API, a set of instruction or communication in human readable form. Now, suppose your friend actually follows that recipe and prepares the tea. The act of using real ingredients, measuring, and heating, that's the ABI. It's the real execution part. So, in the world of software, API, that is application programming interface, is how two programs talk in source code form. Developers can read and use it directly. Whereas ABI, that is application binary interface, is how programs talk after they are compiled at the machine code level. In other words, API is about what can be done, while ABI is about how it is done and when the machine takes over. An API tells the grammar, whereas ABI makes sure your sentence sounds right when spoken by a robot for a while. Now let's talk about why the ABI matters so much. Even though it works quietly behind the scenes. Think about an electric plug. If every country used a completely different plug shape, your devices would never work when you travel. And that's why we have standard plug shapes. They ensure compatibility. ABI plays a similar role in computing. It ensures that your compiled programs and libraries can plug into each other and work smoothly. So when your operating system updates, ABI ensures your existing apps don't suddenly stop running. So there are three main benefits here. First is binary compatibility. Different software modules may be compiled by different people, but they can still cooperate because they follow the same ABI rules. Second, less recompilation. Developers don't need to rebuild everything each time a new operating system version comes out. And third, platform differences. Each operating system has its own ABI, and that's why you can't run a Windows executable file on Linux because their ABIs are different. So, ABI is like a universal socket of the software world, keeping everything compatible. Let's pick inside the ABI and see what it's made of. Think of it like a building made of four strong pillars. Each one ensures smooth operation between software and hardware. First is data type rules. These define how data is stored in memory, what size an integer has, how a structure is arranged, or how memory is aligned. Example, in one system, an integer may take 4 bytes, whereas in another, it may take 8 bytes. So ABI makes sure everyone agrees on which version to use. Second is calling conventions. These defines how functions send and receive information, which values are passed through registers, which are pushed into the memory, who cleans up the stack. For example, in Windows, one function calling convention might clean up the stack differently from Linux. Third is system call interface. This is the bridge between the program and the operating system. So when your program says save a file, the system call interface ensures the operating system understands and performs it correctly. And last one, fourth, the binary format and naming. This defines how executables and libraries are organized. Linux uses ELF format. Windows uses portable executable format, P format. It also controls how function names are stored or mangled in languages like C++. All these elements together make the ABI a full blueprint of how your compiled code lives, talks, and moves. So let's lift the curtain and watch what happens when a call when we call a function in our program. When you write simple function like add say 3 comma 5, it looks harmless, but deep inside several things happen. First, your system decides where to put these numbers. Should they go into CPU registers or memory? Then after the function finishes, someone must clean up either the function itself or the one who called it. ABI defines these responsibilities. For performance, most of the architectures like x86 prefer to pass the arguments or first few arguments through the CPU register because it is faster than accessing memory. Imagine you are passing water from one glass to other. Using your hand, that is register, is quickly than walking to the fridge memory. So every time your function runs smoothly, remember the ABI is the backstage manager, making sure each actor knows their line and timing. Now, here is where ABI really shows its genius. It brings different languages and compilers together. Suppose one developer writes a module in C, another writes a function in Pascal, and third uses C++. Normally, this would be chaos. But if everyone follows the same ABI, they can all talk to each other as if they speak one binary language. Also, different compilers like GCC, CLang, MSVC can produce code that works together because the ABI provides a shared set of ground rules. For smaller devices like ARM microcontrollers, special embedded ABIs like ARM EABI are used. These keep programs tiny, fast, and energy efficient. So whether you are coding for a massive Linux server or a smartwatch, the ABI ensures everything runs in perfect harmony, like musicians following the same sheet of music. Let's connect these ideas to real life systems you must be aware of. Like system VABI. This one rules the Linux and Unix world. It defines how programs run on x86 and x86 64 architectures. It is the backbone of Linux operating system. Microsoft also follows x64 calling conventions. Windows uses ABI for 64-bit programs. It defines exactly how data flows between functions so that all Windows applications and DLLs can cooperate perfectly. ARM also makes use of EABI format. And this is used by smartphones, embedded boards, and IoT devices. It makes programs compact and efficient so that even tiny chips can run powerful software. So whether you are scrolling on your phone or booting up your laptop, ABIs are quietly ensuring that every piece of code performs its role correctly. Just like invisible stage hands during the perfect concert. Now let's discuss what happens when ABI rule changes. And believe me, this can cause a real trouble. Imagine if tomorrow the rules for traffic lights are swapped. Say green means stop, red means go. That would be a chaos, right? Similarly, when ABI changes, old programs compiled under the old rules might crash. They may misbehave or stop working altogether. Even if the source code hasn't been changed, you might need to recompile the programs so that they will follow the new ABI rules. And that's why developers try very hard to keep ABI stable across versions. Maintaining ABI stability is like maintaining peace in the city. Small changes can disturb a lot of systems. So engineers approach it carefully. Now let's visualize the full journey of a program step by step. So you start writing your logic in C or C++. It is readable, clear, and human friendly. The compiler acts as translator. It follows ABI rules to decide how data types are handled, how functions pass information, and how everything fits together. The compiler then produces a binary file, a series of zeros and ones that's made up or that's the machine can understand and execute. Finally, through the system calls and ABI structures, your program communicates with the operating system and hardware to perform real actions. Open a file, draw on the screen, or probably print something. This step by step dance is powered entirely by ABI, and it's the invisible conductor that makes the orchestra of code perform flawlessly. So, to conclude our journey, ABI is like silent engineer or invisible translator of the computing world. It defines how compiled programs talk, share, and run, regardless of language, compiler, or hardware. For developers who work close to hardware or create cross-platform or say cross-platform applications, understanding ABI is like knowing the heartbeat of the machine. A stable ABI means your programs can travel between systems smoothly, be reused easily, and maintained with less effort. It ensures your software world stays compatible, reliable, and peaceful. So next time, when your application runs perfectly across systems, remember, it's not the magic. It's the application binary interface, the unsung hero behind the curtain. Thank you.